Hello and welcome back to the video series about ordinary differential equations. It's a long name and therefore often we just say ODE. And in today's part 4 we will show that any system of ODEs can be reduced to a first order system. This is very helpful because it means that we can describe the theory just with first order differential equations. It also means that we can always use this nice directional field we have introduced in the last video. Okay, but before we start with the formulas, you already know, first I want to thank all the nice people who support this channel on Steady via PayPal or by other means. Only because of your support, I'm able to create such video courses here. And please don't forget, you can download the PDF version and the quiz for this video with the link in the description. Okay, then let's start with the topic of today by looking at an example. We choose that the highest derivative we have is the third derivative. And then this should be equal to the cosine of the second derivative plus first derivative squared plus x. So this is what we would call an explicit ODE of third order. Moreover, the time variable t is not involved on the right hand side here, so it's a so-called autonomous ODE. And now we will show that we can reduce this ODE to a system of ODEs of first order. And this simply works by defining a vector variable y that has the derivatives of x as components. More precisely, the first component should be x, then comes x dot, and the last component, the third component, is x dot dot. So you see, all the functions x here on the right hand side are now written as components of a vector. So instead of 3 functions, we now have one vector with 3 components. And now the idea is that we can rewrite the original ODE, the equation from above, with the help of the components of y. So this means the third derivative of x is now the first derivative of the third component of y. And then on the right hand side, we can also substitute all variables x. Again, the second derivative here is our y3, then the first derivative is y2, and x itself is y1. There you see, this is the whole idea. Now the first derivative is the highest order that occurs. However, now we also have to make the connections between the other components. So you see, y2 dot is equal to y3. And lastly, we have that y1 dot is equal to y2. Okay, and there you see, this is all. This system of 3 equations has exactly the same information as this one ODE where we have a third order for the derivative. However, this was the whole idea because now we can simply write y dot is equal to a vector function v of y. So now you see, we have a nice system of ODEs of first order. So we conclude, if we understand in general the system of first order ODEs, we can also understand higher order ODEs. However, at this point you should ask, what can we do if we have a system or an ODE which is not autonomous? For this, let's simply look at the next example. So let's say we have a similar example as before, but now also t occurs on the right hand side. So maybe we find minus t to the power 4 here. Hence, this is now a non-autonomous ODE, but still of third order. Therefore, we could do the same procedure as before to get it to first order, but still it would be non-autonomous. So we have to do one step more to get rid of this t here. Indeed, we could do exactly the same as before and define the vector y as above. However, now we also have to put in the variable t in some sense. And one thing that works very nicely is to use it as the first variable here in the vector. And if we want to keep the indices as before, we should call it the 0th component. In other words, our vector y has 4 components where we start counting with 0. So we start with y0, then we have y1, y2, and so on. Indeed, if we do that, we can do exactly the same as above. In other words, these 3 equations from above we can just copy here. The only thing to add is now in the last equation our 0th component. So t to the power 4 is now y0 to the power 4. In other words, this is now autonomous because there is no t on the right hand side anymore. However, this means we have to introduce a new equation to describe our t. But of course, this is very simple because we can simply calculate the derivative of t. So we see y0 dot is equal to 1. So in the end, we see this does not change anything. It does not make the ODE simpler or easier to solve, but we see we can transform a non-autonomous ODE into a system of autonomous ODEs. Hence, in short, all ODEs, all explicit ODEs, can be described with this formula here. The only thing that might change is the number of components of y. So this is definitely something we should remember because it explains why in our theory here we only consider this form. So I would say, let's write this down in general terms. Now assume we have an autonomous ODE of nth order. Then we can do the substitution as before and get a system of first order. However, now the variable y has n components. So in summary, we get an autonomous system of n ODEs of first order. And now you know we can do exactly the same if we have a non-autonomous ODE. We simply do the substitution as explained here, which means we get a system of ODEs, but y now has n plus 1 components. Okay, there we have it. The result here is again an autonomous system of ODEs of first order. And this explains why in theorems and propositions we will always take this form for a general ODE. It is not a restriction at all because we can always translate back to the original ODE. So for example, if we have found a solution here on the right hand side, we can simply translate it to a solution for the left hand side. This is no problem at all because you see the translation here is very simple. Okay, I would say in order to get some practice for dealing with ODEs, we will look at some methods for solving them in the next video. Of course, finding solutions is a very important part of this theory here. Therefore, I hope I see you in the next video and have a nice day. Bye!